Hi, I'm Evan, and I'll be presenting an algorithm on optimal measurement configuration in spectral diffractive imaging. And I'm a student at the University of Illinois at Urbana-Champaign. So in this presentation, I'll first introduce what diffractive spectral imaging is, what we use it for, a little bit of how it works. Then I'll show the mathematical model for how images are formed. Then I'll go on to explain how our previous method, or the standard method for acquiring measurements in spectral imaging using diffractive optics at the focal planes, can be suboptimal and give suboptimal reconstructions. Then I'll introduce a cost metric, which we'll use in the greedy algorithm. Then I'll introduce said greedy algorithm and show how we use it to find a better set of measurement locations. And then I'll show some numerical results showing some reconstructions, and also try to give an intuition as to why the greedy algorithm chose the measurements that it did. So diffractive spectral imaging systems use the principle of diffraction, which is when a polychromatic plane wave enters an aperture, the light is split into different components, and specifically for diffractive lenses, it forms images for different wavelengths at different distances from the lens. So for example, here we have a plane wave coming from some source with multiple spectral components. It hits the diffractive lens and is split into its components, and we can move our sensor, either CCD or CMOS sensor, closer or farther away from the lens to obtain images of these spectral components. And this is how we achieve spectral imaging. Also, diffractive lenses have a few advantages over conventional glass optics and mirrors. One of these is that they generally have higher precision due to their fabrication process, which is usually photolithography, and so we can achieve a lot tighter bounds with this fabrication process compared to, say, the grinding used for glass lenses and mirrors. And another advantage is that glass is usually opaque to ultraviolet. So for example, if we're doing spectral imaging of the sun in the ultraviolet spectrum, it's very hard to use glass optics. So now I'll introduce the image formation model and provide some intuition here. So if we take as an example a multispectral source which has two spectral components at wavelengths lambda 1 and lambda 2, and we allow that to propagate through our system through this diffractive element here. If we take some measurement at measurement plane 1, which is the focal plane for wavelength lambda 1, we'll see that we'll have a focused image of the red smiley face here, and then a blurry image also in the same plane of the second source. And then if we move back to the second focal plane for source 2, we'll see that, of course, the second source comes into focus, but the first source is still present as a blurry image. And so you can see here one of the properties of a diffractive element is that you have different PSFs for each source, which change depending on the wavelength and also the distance that you're measuring at. And that is to say, the wavelength of the source. So if we write this mathematically, we'll see that each of our measurements, ym, is a sum of all of the sources blurred to varying degrees, plus some systematic noise. We can rewrite this as a linear system in matrix form, and each of these A matrices is a convolution matrix containing the PSF. And as a note, for convenience, we'll refer to the set of where all of these measurements are made as the measurement configuration. So this measurement configuration for D would have different distances from the diffractive element. So in a lot of previous work, sort of the status quo is to make measurements at the focal planes, which can work well, but in certain situations when you have sources which are very close in wavelength, your focal planes are very close together, and so this can lead to poor reconstructions. And so the reason that this happens is if we actually look at the observation matrix A for a particular measurement configuration D, if the sources are close together, we'll see that we actually get rows which are very, very similar and nearly identical. And so this gives us poor matrix conditioning, and when we try to solve the inverse problem on the previous page, we get bad results. So the question is, can we find better measurement locations through some sort of algorithmic search? Well, before we can answer that question, we need to have some way to compare two measurement configurations to see which one is better. One natural method, or one natural cost metric, would be to basically look at the expected error, the total error over our reconstruction. So this would be the sum of squared errors. It's important to us in this situation that our total error is closed form, so that it makes it easy to evaluate this cost. So in order to achieve that, we need to make some statistical assumptions about the source X and the noise. In this case, we assume that they both have Gaussian statistics, and this leads us to, specifically for map, the well-known Tikhonov formulation, Tikhonov regularization. And so now if we take this map estimate and we plug this back into the cost, then we can see we have a nice closed form for the cost here, which only depends on our observation matrix A, the covariance of the noise, and the covariance of the source. So now that we have our cost function, we can begin algorithmically searching over all possible measurement configurations. But it turns out that an exhaustive search over all measurement configurations is combinatorial, and it quickly becomes intractable for even the simplest of problems. So we need to instead approach this with a greedy algorithm. And so the greedy algorithm that we propose to use starts off like this. So we take we start with our measurement configuration, and we initialize it with n repeated measurements at some set of C candidate planes. And so these C candidate planes can be chosen a number of ways. Usually what we do is just uniformly space them around the focal planes, just so that we have a nice representation of a lot of measurement locations. The next step is to look at each of these candidate planes and find the one that contributes the least to the reconstruction. So basically, if we were to eliminate one of these measurement locations, we look at the one that contributes the smallest increase in cost, or the smallest increase in total error. And then once we've identified which one that is, we eliminate it from our measurement configuration D. So if we repeat this, we keep going until we have only M measurements left, and that's what this picture on the right represents. And so here's just an algorithmic summation of summary of the algorithm. And of course, this greedy algorithm requires much, much fewer cost evaluations than an exhaustive search. So here are some numerical results showing some reconstructions for synthetic data. On the left, we have a two-component source which has been colored to show the green is one source, and then we have another source, or another spectral component, which is very close in terms of wavelength. So this would be a situation, well, as you'll see, this is a situation where using the strategy of taking measurements at the focal planes can give you poor results. So here in this first column, we see a reconstruction for source 1 and our reconstruction for source 2. And if you'll notice, we have some streaks which seem to be running the wrong way. Our source 2, all of the streaks are running from top left to bottom right, but we have some in the reconstruction which are running the opposite way. And these are actually bleed over from source 1. So if you remember earlier, I mentioned that for the focal plane measurement configuration, you end up with rows which are nearly identical, and so you don't get very good measurement variation here. So this is what's causing the bleed over. But now if we look at the set of measurement planes, or the reconstruction obtained from the measurement configuration derived from our greedy algorithm here, you can see that we no longer have this bleed over issue. And so on the next slide I'll give you some intuition as to why this happens. So this is the set of measurement locations that was chosen by the greedy algorithm for the reconstructions shown on the previous slide. So what this is this is the distance from the sieve, and the height of the bar represents the number of measurements made at these particular candidate locations. So here we started off with 31 candidate locations, and we initialized with 3 measurements at each one, and then we iterated until we only had a very small number of measurements total. And you can see here these are the candidate planes which correspond to the focal planes for the 2 sources. And so if we look down below, these are the PSFs that are associated with each candidate plane for source 1 and source 2. If we look at the PSFs for close to the measurement location, and it's kind of the same for lambda 1 and lambda 2, I only show it for lambda 2 here, you can see that they're very similar. So again, you don't get very good measurement variation. But what the algorithm chose instead was to move the measurements towards the left and to the right and sort of split them. And if you look here, we can see that the PSFs they're noticeably different. They're actually slightly blurrier, but you have better variation. And so basically what our greedy algorithm is trying to do is it chooses measurement locations which give you sometimes greater variation at the expense of a slightly blurrier PSF. But overall, it tries to choose a configuration which gives you a minimized error. And so this is the intuition for why the algorithm does what it does. So this is the end of my presentation. I hope you are interested in the algorithm, and thanks for listening.